Hi, I'm Kenan, and today I'll be presenting about UAV communications. The use of UAVs has become increasingly widespread, and thus there's been a lot of research done on robust, efficient, and secure communications between UAVs. UAVs mainly communicate wirelessly, and for hobby UAVs, it may be handled through short-range communication technologies such as RF, Bluetooth, or Wi-Fi. However, for commercial communications, larger amounts of telemetry data needs to be sent and received over a longer distance. Hence, for those situations, satellite communications or cellular networks may be employed instead. Typically, the network structure of UAVs consists of the following parts: ground control stations, base stations, and the UAVs themselves. The GCS acts as a central communication hub for UAV operations. As machine-human interfaces, it allows human operators to manage complex flight operations easily, as the GCS facilitates any necessary communication, control, and data processing in the background. Communication structures in UAV swarm and multi-robot environments can be largely classified into two categories: centralized and decentralized. Both have their own advantages and disadvantages, and it may be hard to discern which approach might be the best, and a hybrid strategy that incorporates both aspects is also possible. For centralized communications, it relies on a single main control unit to coordinate the actions and information of all UAVs connected to it. This is a very simple structure to set up and is highly performant in small networks due to having minimal overhead. An extended star topology is also possible by attaching another star network to the main network. However, the main disadvantage would be a single point of failure and high central bandwidth requirement for the main node, which can cause congestion latency. In contrast, a decentralized network relies on a peer-to-peer network structure. This has high scalability and reliability, as each UAV can individually enter and exit the network and make decisions by itself. The main disadvantage being a more complex implementation and higher energy consumption. Similar to how TCP/IP packets work, UAVs employ communication protocols to send data fast and efficiently due to their low onboard resource nature. They typically cover the application and presentation layer of the OSI model. Common protocols currently in use includes Cipher, MAVLink, Uranus Link, and STACKNET 4586 for military use. Between Cipher and MAVLink, here you can see the differences in their packet structure. Cipher being more complex and can handle higher concurrent devices and more transport layer technologies, while MAVLink is simpler with slightly higher overhead. Overall, protocols for UAVs all have very similar architectures, where they have communication methods for one-to-many with publish and subscribe, and one-to-one with client-server. The main differences will be their performance, ease of use, and native features included. Communication security is one of the areas of research for safe and secure operations. The main areas for security includes confidentiality, integrity, availability, and authorization and authentication. Confidentiality meaning communicated sensitive data should be protected from unauthorized third parties. Integrity, where information sent must be tamper-proof and packet loss resistant. Availability, where communication links must be always available when requested. And finally, authorization and authentication, where a user's privilege for accessing any system resource must be identified. The main challenges for security would be the large vulnerability space that can be found. The diagram shows some of the possible attacks a malicious actor can perform. This is a field that is constantly being researched, as it is a challenging problem due to low onboard resources, where lightweight and secure cryptography solutions are required. Now we move on to some future research topics. One methodology proposed by researchers is that UAVs can be integrated with blockchain technology to address the integrity issue. Blockchain, which is a decentralized database, prevents data tampering by linking each new data node with a cryptographic hash of a previous node. However, the main disadvantage is that it is computationally resource intensive, meaning a higher power requirement which is not desirable. It can also have increased latency due to more data being sent for redundancy and consensus verification. Some research has been done to mitigate these problems, such as adopting a lightweight cryptographic algorithm called hyperelliptic curve cryptography or using a proof-of-stake consensus method. However, more has been done for practical real-life implementations. Next, future adoption of the 6G mobile networks is expected to significantly improve the operation performance of UAVs. Compared to commercial 5G networks, 6G is able to provide higher theoretical data throughput with higher range, higher energy efficiency, and lower latency using a better satellite technology. What this means is that UAVs won't be bottlenecked by existing data links, and we can shift more computational and data-intensive tasks such as blockchain and AI integration to an edge computing platform. The addition of AI would help better optimize energy consumption with enhanced decision-making and flight path optimizations. However, the feasibility of 6G integration is still in their preliminary stages and is not commercially viable, especially since 5G is still in the midst of rolling out.